Greetings, mathletes, and welcome back. So in the last video, we were talking about estimating areas using a bunch of little rectangles, right? And we saw that there was different ways to do that: right-handed, left-handed, midpoint, and they all give you estimates. None of them actually got anything exact. Um, and we did this with that. The problems we were working on had a small number of rectangles, right? I think the most you were asked to actually compute was an area with 4 rectangles. But what do you do when you have 600 rectangles? It's certainly doable, but God, I mean, that's got to be one of those things that it's going to take a while to get through all that, and that's pretty tedious. And honestly, mathematics is an active pursuit of laziness. And so mathematicians wanted to find a way to do this stuff a lot quicker because yeah, we mathematicians can plow through a bunch of arithmetic, but I don't know any mathematician who actually enjoys it. So let's see if we can let's see if we can understand some of these shortcuts here, and go from there. Okay, so the way we're going to be handling these sums is what's called sigma notation. Sigma is a Greek letter. The lowercase sigma looks like that. And you see that one pop up in stats for the standard deviation quite often. Those of you who are math majors will see it show up in other contexts later on. The one we're going to be using is actually a capital sigma. And it looks like that. I know a lot of the time when people substitute Greek letters, they use that for an E, but that's actually an S, is what it really is. In any case, this is how the notation works. Okay, so you have some term that we're going to describe in terms of k. So you have ak, a sub k. And then what you do from there is you note what the values of k are going to be. Actually, let me get rid of this so it doesn't look like it's part of the notation. So I'm going to say we want everything from k equals 1 to let's keep it small for right now so we can just focus on the concept, right? And so what you do is one at a time you substitute k for all of the numbers between 1 and 4. So this would be a1 plus a2 plus a3 plus a4. And the ak and quite often bk, that's not a b. Try that again. There we go. AK and BK are just used in terms of generic terms. They're called terms because each one of these is a term. So this is a generic term. If I wanted an actual term, I might have something like this. So the sum from k equals 1 to 4 of 2k minus 3. Right, and a lot of the time when you have more than one term in the summand, that's what that's called, the summand. Right, the things that you're adding up are the summands. So this is the summand. What this means is one at a time, you're going to take k out and put 1, and that would be your first term. Then you're going to take k out and put a 2. And that's your second term. And then you take k out and put a 3. And that's your third term. And finally we get up to 4, and that's how we know when to stop. Right? And then you just add everybody up. And you can see, I mean, none of these terms are very difficult to compute. Right? It's a multiplication and minus 3. That's it. That's all you have to do. But there's a bunch of them. And if this wasn't 4, if this was 40 or 400, this would be insurmountable. Right? I mean, you could do it, but it would take you all day, just, real carefully. And then if you made a mistake somewhere, God help you, you're never going to find it. So we need to find some ways to add these things up in a more efficient manner, right? As far as that goes. So, and then finally, Well, I haven't actually worked this one out. Let's see if we can work it out real quick just for the sense of completion here. So 2 minus 3 is -1. 4 minus 3 is 1. 6 minus 3 is 3. And 8 minus 3 is 5. So those two cancel out, and I get 8. Right? So what I did is I just worked out each term one at a time and added them all up. And you saw it actually did work fairly quickly. But the stuff we're going to be working with, sometimes we don't know what the upper index is. Sometimes it's just an n, right? And so we need to be able to deal with that to be able to deal with some of these formulas. And so we're going to have some formulas that tell us a quicker way to add these things up. Okay, so let's go ahead and get rid of that. And let's say I have something like this, but in a different color. Okay, let's say I have the sum of k from k equals 1 to n. Now you notice that means n is a number. We just happen to not know how high it counts up, right? So this is a good way to get a hold of a formula. This would be 1 plus 2 plus 3, right? So I'm just replacing k with the number I want. And this is going to go all the way up to n minus 1 plus n, right? So it's all the numbers up to n. Now, some of you may have seen this before, but it turns out if I decide to multiply this by 2, right, that's the same as adding it to itself. And since we can add in any order we want, I'm going to add it this way. And then at this end, it'll be plus 1 and plus 2, ... And there'll be... Now, one of the things that people notice, if you add them from opposite ends like this, each term comes out, that n plus 1 is n plus 1. N minus 1 plus 2 is n plus 1. N minus 2 plus 3 is n plus 1. And all the way to the end, right? They all end up being n plus 1s. Right? And how many are there? There's actually n of them, right? Because I can count them. 1, 2, 3, right? All the way up to n. So there's n of these things. So this whole term just turned into n times n plus 1. Now, we multiplied that by 2. Right? So that means if I want the actual sum, I have to divide it by 2 to undo it. So I end up with n times n plus 1 over 2. So that means the sum from k equals 1 to n of k is equal to n times n plus 1 over 2. Now, how do we use this? Well, it's a good thing you asked. Let's say I have the sum from k equals 1 to, let's pick something. I'll just pick 50. Right? Certainly that's something you could add up. You could probably just pull out a calculator. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to 50, right? No big deal. It's just time consuming. But you notice the upper index here, n, is 50. So what that means is I can use this formula with n equal to 50. So this is now 50, and 50 plus 1 is 51, divided by 2. Right? That's kind of fun. Well, that's not too bad. 50 times 51, so that's, was it 2,550? Let's make sure. 2,550. So this is 2550 divided by 2, and that gives you 1275. And so that's a whole lot easier than plugging it into your calculator, adding one thing at a time as we go, right? And so we're going to have formulas like this. This is actually the only one I'm going to show the derivation of it. But this is one of our first formulas that we're going to look at. Now, I'm going to talk about properties a little bit, and then we'll put in the formulas. Then we'll have our full tool set, and then I'll show you how to use the tools. Okay, so, yeah, there we go. Okay, so some properties. Okay, so if you have a sum, and you actually have two terms in this sum, and they're either being added or subtracted, what you can do is split it up as two sums. So I can take this as the sum from k equals 1 to n of ak. So I can work that one out. And whatever that sign is, either plus or minus, you're going to get the same sign here. And that's k equals 1 to n of bk. My handwriting is really not doing so well today. Right, so you can split it up into two things. Another property is that you can pull a constant through a sum. Basically, if you think about it, if you have a bunch of terms all listed out and you have the same factor in each term, you can factor that out. And that's essentially what we're doing. We're factoring something out. So if you have some constant c times ak, you can pull that constant to the outside and just look at that, right? So you can pull that constant through and look at what's left and take the sum of that. These are all the things that are going to allow us to simplify this down to where we can use formulas. And then the last thing is actually, these are more properties. This next one's more of a computational. If I have a sum from k equals 1 to n of just a constant, right? That means there's nowhere to plug in k. So what you get is that constant over and over and over and over again. It ends up being n times that constant, right? Because it shows up n times. So there's our first computational formula. Well, I guess it's not our first because we actually derived the other one. The next one, and I kind of wish I'd put that over here. Let's see if I can move it. I can. There we go. I'll put it here so we can have a list. Okay, so the next one, and you really should copy these down because we're going to be using them in the next, in the examples here. If I have the sum from k equals 1 to n of k, well, we just found that formula, right? That was the n times n plus 1 over 2. Then there's also a formula for the sum of squares. And that formula is n times n plus 1. And then there's a third factor here, which is 2n plus 1. I remember this third factor because it's the sum of the first two. If I add n to n plus 1, I get 2n plus 1. That's how I remember it. And that one happens to be over 6. Then we have the one for cubes, and these actually go farther than this, but this is what we'll need today. Which is, it actually turns out to be the square of the linear model. So it's n times n plus 1 over 2, but I'm squaring it. Right? So these are the formulas. These are going to be your computational formulas. These are the properties, and they're kind of like formulas, but they're telling you what you're allowed to do when you manipulate things. This is how you actually come up with numbers, right? So these tell you what things you can do to manipulate it. This tells you how to find the number at the end. Okay? All right. So make sure you have those written down. If you need to pause it here for a second and jot all these formulas down, I think it's a really good idea. The first two you're probably just going to get familiar with by using the properties. The other four formulas, again, it's going to be using them. I find it harder to remember formulas myself, so I understand. Write them down. Okay, so let's go ahead and take a look at an example now. Okay, so we saw some algebraic examples. I want to at least show you one example where you have something like a trig function in here, just so you know, just so it doesn't look too crazy. The ones that have trig functions, generally n is a fairly small number, so you can just compute them one term at a time. Let's do k equals 1 to, let's make it 4 of cosine k times pi, right? So if we're looking at something like this, what you would end up doing is just like anything else, you're going to plug in values for k one at a time. 1, then 2, then 3, and then 4. So we're going to have 4 terms here. So this ends up being cosine pi plus cosine 2 pi, right, when k is 2. And then when k is 3, it's cosine 3 pi. And then when k is 4, it's cosine 4 pi. Now, if you remember your values of cosine, cosine pi is -1, cosine 2 pi is 1, cosine 3 pi is -1, and cosine 4 pi is 1. And so if I add this series together, this excuse me, these 4 numbers, I get 0, right? So it could come out to 0 very easily. Now, let's take a look at something that has a little more meat to it. And, yeah, where'd I put it? Okay. Yeah, so the ones that have small values for n, like here where n is 4 or 5, you're probably expected to just write out each term and then collect everything together into a number. However, if you're given something like this, right, that's a little bit different. That's a lot of terms to write out. To write out 50 terms, odds of you getting through that without making some mistakes somewhere are pretty small. So let's go ahead and see what we can do here. So I have a rule that says I can pull a constant out. So I'm going to rewrite this way. And this is k equals 1 to 50 of, well, I pulled the 3 out, so it's just k now. Well, I have a formula for that, right? So what this is going to be is 3, and I'm going to use some interesting notation here, times n minus, or n plus 1, excuse me, over 2, and this is going to be evaluated at n equals, well, n is 50, so this is at n equals 50. So we just need to plug this in. So this is 3 times 50 times 51 over 2. Right? And so really, that's just a calculator problem. I mean, you could work it out by hand also. In fact, I think we just did that in the last problem. Times 3. So that ends up being 3,825 altogether once we multiply it by 3 and do the whole business. But you notice we didn't even have to touch any individual terms. We could jump straight to formulas and come up with the answer a lot quicker this way, right? So these formulas are kind of nice. All right, so I want to take a look at one that has a little more meat, and this one's going to be for you guys to work on. Let's see here. Let's go ahead and do this. Let's do this. There we go. Let's do the sum from k equals 1, where did I put it, to 60, of 3k squared minus 2k plus 1. Right? So let's see if you can manipulate this so that you can use your formulas and come up with an answer. So take your best stab at it, and then when you either hit a wall or come up with an answer, go ahead and push play again, and we'll take a look at the solution. Okay, so let's go ahead and take a look here. So the strategy you want to take with these is to split them up so you can get the variable by itself each time. And I'm calling it the variable, but it's really the index. It is behaving like a variable though. So let's see what we can do with k. We want each k by itself. So that means I can split these all up, and I'm going to do it all in one move here. I'm allowed to split them up by term, and I'm allowed to pull constants through these. So what that means is I can change this to 3 times the sum from k equals 1 to 60 of k squared minus 2 times the sum from k equals 1 to 60 of k, and then plus the sum from k equals 1 to 60 of 1. Let's make that look rather 1-like. Okay, so really the idea here is to get a hold of these pieces. This one we can do in our head because you just have to take the upper index and multiply it by your constant. But these have formulas. So this one, since it's k squared, it's going to be 60 times 61, and then the last factor in this product is 60 plus 61. So that's 121 over 6. Excuse me. Let's go ahead and get a hold of this one now. I'm going to use a calculator for this. Okay, so 60 times 61 times 121 divided by 2, or excuse me, divided by 6, wrong formula, gives me 73,000. Is that a 10? Well, my eyes are getting bad. 810, right? And remember, that's this part. So if that's this part, all I have to do is multiply that by 3 to get the sum of the first term. Then here, this is going to be 60 times 61 over 2, right? That's the n times n plus 1 over 2. That's the sum of k, right? And if we go ahead and multiply that out, I get 1830, right? And remember that was times minus 2 plus, and then the last one, well, n is 60, so it's n times c. c is 1, so this is just 60, right? I don't have to do anything special. And then from there, it's just a matter of just its order of operations from here on out, right? So I got 3 times 73,810 minus 2 times 1830. It just dawned on me I probably should have used the digital calculator for this, but I'm pretty sure you guys can plug in multiplication and addition and subtraction. So what we end up with is 217,830. Right, just taking it one piece at a time. Right, so it really is, it's going to boil down to pretty much the same thing each time. You're trying to get the k's isolated so you can use formulas. And then you just put everything else back in around it. You know, you are certainly welcome to just write out every term from 1 to 60, but that is not going to be the time-friendly way to do these, right? Now, why are we talking about these? Why are these important? I had mentioned the the sums we were taking. And it's actually, those sums are called Riemann sums. I'm trying to remember if I meant to mention it in the last video. I'm not sure if I did on the redo. But when you're estimating one of these things from A to B, right, and you come up with these rectangles, right? You end up with an evaluation point, right? And we'll call those we'll call the evaluation points C1, C2, all the way up to Cn, right? Whatever they happen to be. The way you get to those, you end up with your f of ck, right? Those are all the different heights. Now you also need the width of the rectangles. The width of the rectangles was delta x, right? And what we are doing is we are adding all of these up from k equals 1 up to however many rectangles we have, right? So now if I look at these evaluation points, what's really happening when I find an evaluation point is I find my first evaluation point, right, C1, and then what I add to it is delta x, right? Because if I start here, if I want to get to the next point, I have to add delta x to it, right? To get from here to here, that's plus delta x. So it's C1 plus k times delta x. And remember, delta x we found was b minus a over n. Okay, so now we have more of a formula. So our CKs are now C1 plus k times b minus a over n. And C1 could just be a if I'm using a left-handed rule. It actually doesn't matter which side you start with. So our CKs are a plus k times delta x. Okay, so that changes the formula to f of a plus k times b minus a over n, right? That's that's getting ugly, isn't it? And then times your delta x. So that's again times a b minus a over n. Remember that b, a, and n are all just numbers. So this actually isn't, when you put numbers in here, it collapses a lot. And the sum is from k equals 1 to n. Well, we want to know, if we want an exact, if we want the exact area underneath a curve, what we do is we use an infinite number of rectangles. The only way to get a hold of that is to take the limit of this whole thing as n goes to infinity. So limits are going to come back up. We're going to have some algebra coming back up. And by the way, this is the definition of the definite integral. When you take that limit, your delta x becomes a dx, and then you have your function. What we're going to be building into is how to get around using these summations to find the area every single time. This is I'll say this too. This is important more for theoretical reasons right now, but when you get to your second semester of calculus, these sums get used a lot. In fact, there's a good portion of the semester dedicated to how to compute sums and different types of sums. So so they are important. But where we're headed next is how to get a hold of these guys, right? How do you get a hold of that definite integral? How do you find the area between two x values between a curve and the x-axis? So in any case, let's see where to go. There I am. That pretty much wraps it up for today. So until next time, keep your pencils and your wits sharp.